Section 2.1 is all about properties that relations might or might not have. We met several examples in the previous section. It's time to see some properties. So here are the definitions. We're going to work through them one by one. We're thinking about a relation R on a set S. So the first one is R is reflexive if, for all x in S, x is related to x. So it says that each element is related to itself. It's a good property to have. Maybe you can think about examples from the previous video which have that property or don't. Next one, we say that R is symmetric if whenever x is related to y, y is related to x. So if I'm drawing arrows for my relation, then I have x related to y, I also have y related to x. So any arrow that I draw is a double-headed arrow going in both directions. And again, we saw some examples where that was the case, and we saw some less pleasant examples where that's not the case. I like this one because it lets you turn things around. If x is related to y, then y is related to x. That could be useful. Now the third one is anti-symmetric, and there's maybe a surprise here. Anti-symmetric is not the opposite of symmetric. That's an exercise to check, I suppose. Here's the definition. We say anti-symmetric if whenever x is related to y and y is related to x, then x is equal to y. So you might have expected the rule here to just be that that never happens, but this rule does permit the case that x could be related to itself. This is slightly funny. If x is equal to y, then this says if x is related to x and x is related to x, then that's okay. So you're allowed to have some elements that are related to themselves, maybe all of them, maybe none of them. There's this whenever here, you see? So it's not actually insisting that any element is related to itself, it's just permitting that. Plus, the main idea here is that for two different elements, you're not allowed to have that relation in both directions, like in the picture up here for the symmetric case. So it's almost an opposite of symmetric, but not enough that I want to describe it as the opposite of symmetric. It's possible to be both symmetric and anti-symmetric, something we're going to see in a second. Lastly, R is transitive if whenever x is related to y and y is related to z, then x is related to z. So if I have three elements x, y and z, if I have these relations, these elements of the relation I suppose formally, then I also have this one, x related to z, the sort of shortcut from x to z. This is good because this lets you join them together so that if x is related to y and y is related to z, then you can sort of carry over the relation from x to z. And again, you can probably think of examples like this. I think my example in my head for this is if x is less than y and y is less than z, then x is less than z as a result. We can go from that pair to that conclusion. And that's called transitive. So 4 properties there, and do watch out for the subtle difference between symmetric and anti-symmetric. Let's look at some examples. So we saw 3 trivial examples in the previous video. As a reminder, there was one where everything was related to everything else, there was one where nothing was related to anything, and there's one where each element is only related to itself. So that last one is an example which is reflexive because everything is related to itself. But of course the one where everything is related is an example of a reflexive relation as well. I want to look at the one where nothing is related. So it's not hard to draw a picture, I suppose. Here we go, 1, 2, 3, 4. There's the picture we had before with no arrows because nothing's related. This one is symmetric because of the whenever. The whenever in here says whenever x is related to y, and I can stop reading because x is never related to y for this relation. So then y is related to x. Fine, okay, I suppose so, if you like. This is an example of vacuous truth, where the hypothesis is never true, so it doesn't matter what the conclusion is. We've got more on that in the chapter on logic, because horror upon horrors, this relation is also anti-symmetric for sort of the same reason. It says whenever x is related to y and y is related to x, well, that never happens for the relation where nothing is related. So I can conclude x is equal to y, I can conclude x is not equal to y, I can conclude x is 3. I mean, it doesn't matter. So this is an example which is both symmetric and anti-symmetric. It's not very nice, is it? So there's an invitation there to think about the other properties and the other relations that we looked at last time, including that chess one, which I tried to set up so that it wouldn't do any of these properties. Let's quickly think about that together. So thinking about the chess one, which is A related to B if A has ever beaten B at chess. Is that reflexive? Well, depends whether you think every chess player has at some point sat down and beaten themselves at chess. The jury's out on that one, I suppose. I'm going to claim that's not true. We say that R is symmetric if whenever, in this case, a chess player has beaten another one, then also that chess player has beaten the first one. And they do play a lot of chess against each other, but I don't think it's true that whenever A has beaten B, B has beaten A at chess at some point. I think some of them are just better than others. We say anti-symmetric if whenever a chess player, whenever that's happened, a chess player has beaten the other and the other has beaten the first, then it must be the case that we were just talking about one chess player playing against themselves. And I don't think that's true either, because I think there are examples of pairs of chess players where A has beaten B and also B has beaten A, and yet they are not the same person playing against themselves. I just think they've played a lot of chess games. And in the last case, transitive would be if whenever A has beaten B, B has beaten C, then A has also beaten C. And I don't think that's true, because I think sometimes A and C might never have met each other, let alone played chess, and let alone got the right outcome. I should probably look up some chess players to find an example of some obscure chess players A and C who have both played chess player B, with A beats B and B beats C, but A and C, A hasn't beaten C, but I haven't looked that up. Maybe you'd like to. Okay, so we've got an example where none of these relationships hold. That's obviously not what we're interested in. We're interested in cases that do lots of these things. So I've got some examples like that as well. Let's talk about these. At the top there, I've got less than or equal to, which is a relation on the real numbers. That's reflexive, anti-symmetric, and transitive. I think reflexive is easy to check. That's the claim that x is less than or equal to x for any x. Anti-symmetric is not too bad. Let's write it out though. If A is less than or equal to B and B is less than or equal to A, excuse me, let's make that a little bit better, less than or equal to A, then, and my conclusion is supposed to be A is equal to B. And that's just true, isn't it? That's a true fact about less than or equal to. So that's what I mean by anti-symmetric. That in this case, because the relation is reflexive, it's actually true that whenever A is equal to B, this does happen. That needn't be the case. For example, if you're reading ahead, you'll notice that I'm also claiming that the relation A less than B is also anti-symmetric. If A is less than B and B is less than A, then A equals B. And you might be quite upset by that because, well, if A equals B, then neither of these are true. But I'm not saying it that way round. I'm saying if both of these facts are true, then A equals B. And of course, for the less than relation, these things are never simultaneously true. This never happens. which means that my statement of the form if this then that is true as a statement because there are no counterexamples. If you like, I'm saved by this if at the front, as they say, big if true, and this fact is not true, so we cannot deduce that it's big. By which I mean that the fact that the thing in brackets is never the case means that this is a true statement. It's an example of vacuous truth again. We didn't talk about not equals to last time, but I claim that it's not reflexive because it's not the case that for all x is not equal to x. That's a bit of a tongue twister. It's not anti-symmetric or transitive, but it is at least symmetric. Good. If x is not equal to y, then y is not equal to x. You get it both ways around. And finally, equals, which is a bit of a confusing one because we've sort of used it in our definition. I suppose we have equality of elements, but that itself is a relation on R with some nice properties: reflexive, symmetric, and transitive. Okay, one more example, and this one's quite important. This is congruence modulo n. I'm sure you're going to see lots about modular arithmetic during first year. Here's my definition. I'm defining a relation on the integers by saying that a is related to b if and only if the difference between a and b is a multiple of n, where n is some integer that's at least 2. I claim that this relation, to do with the difference being a multiple of n, is reflexive, symmetric, and transitive, which you'll remember those are the properties that the equals sign has. It's in a good company there having those properties. Let's check it with a proof, just to work through the definitions. So for reflexivity, we need to check that every element is related to itself, and that's true because an element being related to itself means that the difference between a and a should be a multiple of n, and the difference between a and a is obviously 0, which I claim is a multiple of n because it's 0 times n. That's a multiple. For symmetry, we need to check that if a is related to b, then b is related to a. So using the definition of what does it mean for a to be related to b, it must be the case that a minus b is some multiple of n. And we are interested in b related to a, which is a statement about b minus a, which is minus kn. And so that's also a multiple of n, or allows negative multiples of n. So b is related to a. So it's got symmetry as well. Last one is transitivity. And so we have 3 things here, a, b, and c. The thing we're interested in is if a is related to b, the difference is a multiple of n. If also b is related to c, then that difference is a multiple of n. We are interested in whether the difference between a and c is a multiple of n. And of course it is, you should add those things together. So the maths works like this. If a is related to b and b is related to c, then we have 2 facts, and I propose that we add them together to cancel the b's. If we do that, then we get a minus c, and we get a beautiful multiple of n, and we conclude that a really is related to c. So we have a relation then, defined using differences, which is reflexive, symmetric, and transitive. The same properties that we saw the equals sign has. This is an example of something called an equivalence relation. It identifies something about the objects in the set that is the same. And our next section is going to be on equivalence relations, equivalence classes, and partitions.